Hello, in this video I'm going to be discussing the vector triple product. This is a way of multiplying three vectors together to get another vector. We've already discussed the scalar triple product, in which we have three vectors and we get a scalar. In the vector triple product we get a vector. So what is the vector triple product? Well, it is what's shown here. The cross product of a vector A with the cross product of two other vectors B and C. So this is similar to the scalar triple product, except for we take the cross product here rather than the dot product. And there's a formula that simplifies this vector triple product, or applying the cross products twice in some sense, which is on the right-hand side of the formula here. One thing that you should note is that the cross product is not associative, meaning that you can't change the place of the brackets or remove the brackets entirely. If you were to take the cross product of A with B first, and then the cross product of that with C, you would get a different result. And so vector triple product is specifically this. So at this moment, the vector triple product may seem a little bit unmotivated. It does appear in some applications, which is the reason to study it. It appears in some equations involving elastics or elasticity, and also in electrodynamics. But for the moment, we're just going to study what this vector product is and the formula for it. So the formula shown here for the vector triple product can be proven simply by writing out the components of three vectors, A, B, and C, and then computing the triple product and checking that the two sides are equal. This is actually an exercise on one of the problem sheets, but it's not necessarily particularly illuminating to do this. It's just a calculation that shows that they're equal. This formula is sometimes called the back-cab formula, B-A-C-C-A-B, as a mnemonic to remember it, because the right-hand side is B times the dot product of A with C, and then C times the dot product of A with B. So back and cab. Okay, so another sort of explanation of this formula. Why is this vector triple product with the two cross products equal to the right-hand side of this equation? Well, if we consider V equals A cross product with B cross product with C, we know that that would be a vector perpendicular to both A and the cross product of B with C. But the cross product of B with C is perpendicular to the plane containing both B and C, and so that means that V, the triple product of A, B, and C, has to be contained in that plane containing B and C. And this means that V must be a linear combination of the two vectors B and C. That is, we can write V as a constant times B plus a constant times C. And that is what we have in the formula. We have the constant here is the dot product of A with C times B, and the scalar, I should say, is the dot product of A with C times B, and then the scalar multiplied times C is negative the dot product of A with B. So that explains why we can write this triple product as a combination of B and C, but the exact form of the two scalars that are multiplied times B and C is not explained by this. You have to really go through the computation in order to see that. So let's just do a simple example of computing a vector triple product. So we have three vectors, A, B, and C, which are given, and we want to compute this vector triple product. Well, we use the formula from the previous slide, the back-cab formula. This is B times the dot product of A with C minus C times the dot product of A with B. And so what we need to compute are the two dot products. And you can see this is a lot easier than computing a cross product twice, which is more difficult computation. And so let's compute these dot products. Go back so you can see what A, B, and C are. So the dot product of A with C, A is just I, and so we just get 1 times negative 1, negative 1. We take this dot product. The dot product of A with B is going to be 1 times 2, so we just get 2 for this one. Okay, and so this vector triple product is equal to b, which if we write in the column vector format is 2, -1, 0 times -1 minus c, to underline that one, c, which is -1, 3, 0 times 2. And so if we work this out, we have -2 plus 2, so the first entry is 0. And then 1 minus 4, or sorry, minus 6, and so the second entry is -5, 0. So this is the vector triple product of these three vectors, A, B, and C. All right, so this is simply an example showing how this formula, the back cab formula for the vector triple product, allows us to compute it much more easily than computing the cross product twice. I'm going to do one other example using the triple product, which is shown there. And so we have this expression for any vectors A, B, and C, which is C cross product of A cross product of B, C. And we want to simplify this product. So we can use the vector triple product formula. That what's in parentheses here, the outer parentheses, is the vector triple product of A, B, and C. And so we use the back cab formula. So, we have C. And then in parentheses we have B times the dot product of A with C. That's the back part. Minus C times the dot product of A with B, the cab part. Okay, and so we have this formula once we've used the vector triple product formula. And now we can use the distributive law, which we remember holds for the cross product. One of the fundamental properties of what we mean by a product, that the distributive law holds. So we have that C cross B times A dot C. When we distribute the C in here, we get the cross product of C with B minus C cross product with C times A dot B. And one of the properties of the cross product is that the cross product of a vector which is with itself is 0, so the second term is 0, meaning that this simplifies to the cross product of C with B times the dot product of A with C. And so this is a simpler expression for this expression on the left, which involves 3 cross products. Okay, so this is a brief introduction to the vector triple product. Another type of product we can use the 3 vectors. In the last video in this section about vectors, we're going to look at some additional applications using vectors.